In this lesson, you will be able to calculate the pH of a buffer. Okay, so here's the generic equation. HA plus water makes H3O plus A minus. This H3O plus can be H plus, of course. They're the same thing. So Ka would be H3O plus, A minus, and HA. Remember, if these two are equal, the acid and its conjugate base, Ka is going to be H3O plus, right? But what if they're not equal? Then we can have to just plug in whatever you have and you can find the pH that way, right? That's how you get the pH of a buffer. You find the Ka, you find how much you have in the beaker, and then you can get the pH. Okay, but we're going to derive a formula that is even easier to use so we can find the pH of a buffer. So to do this, we're going to go ahead and rearrange the formula a little bit. We're going to put these two on one side. So this is Ka equals H3O plus. We're going to put A minus here and H plus. And I just move them over, okay? Nothing big. Okay, what we're going to do is we're going to log all of this. So we're going to log this one, log this one, log this one. We're going to get the negative log to get the pKa, okay? So we're going to do negative log of this. We're going to do negative log of this, negative log of H3O plus. And then if you're multiplying in logarithms, it's the same as adding, plus, and negative log of this, which is right here. Okay, so rearranging the equation, we have negative log of Ka is called pKa. Negative log of H plus is called pH. Negative log of this is just negative log of A minus. A minus over HA. Okay, so it looks like we have a formula here. We're just going to rearrange it a bit because we want to get the pH of your buffer. Why don't we put the pH on the one side? Okay, so I'm going to put, so pKa equals pH plus and a minus. Okay, so this right here, A minus, okay, first this is the acid, HA, and you should know this is the conjugate base, right? So I'm going to change it to write pKa equals pH plus negative log, this is the conjugate base over the acid, okay? So pKa equals pH, a plus and a minus becomes a minus, log of base over acid. Okay, next I'm going to put pH on one side by moving this whole thing over there. Okay, so pH is equal to pKa minus here, so it becomes plus log of base. I'm going to use just B for the base. That's the molarity and acid. Okay, so this right here is your formula. All right, so first let me just tell you a little bit about the bracket. The bracket means molarity, which is equal to moles over liters, okay? Divided by, this is also molarity, which is equal to moles over liters. Since they're in the same container, they will have the same number of liters. So if you want, you may put moles in there as well. So that can be moles, or you can put in molarity. Either one will work. Okay? This equation is the Henderson-Hasselbach equation. It's very, very easy to use. To get the pH of a buffer, all you have to do is find the pKa of the buffer, and to get the pKa, just look at the conjugate acid and you look at the Ka here and you just negative log that. That's the pKa. Then you add it to the log of the molarity of the base over A. This Henderson-Hasselbach is to get the pH of any buffer that you'd like. Okay, if The conjugate base equals the acid. These two will cancel. Becomes 1. What's the log of 1? Yes, it's 0. So pH equals to pKa. Just like what we learned before. If you guys remember here, this is HClO. This will be the pH if these two numbers are equal, because they cancel each other out in the Henderson-Hasselbach equation right there. Okay, this is a problem. So easy. What is the pH of a buffer? As soon as you say that, you're going to write pH of a buffer is equal to pKa plus log of Ba. And the way I remember it is Ba, Ba, black sheep, have you any wool? Yes, sir, 3 bags full. So Ba. Okay, so you just find it. What is the pH of a buffer? 0.12 molar lactic acid. So that would go in the A, right? So equals plus log, plug in A down here, 0.12 molar. Okay, or that's the same writing, and 0.1 molar sodium lactate. So here you're confused because why is the sodium there? Remember, this is an electrolyte. When it goes into water, the Na plus dissociates from that negative. So this is not doing anything. This is your ion right here. That is the conjugate base because it's missing. If you look at them, they're different by 1 hydrogen. They're conjugate pairs. So then that number is the base. This is the conjugate base. So that goes here. Okay. Then you look for the Ka of lactic acid. You can look in the chart. This one, they gave it to you, so just use it whenever they give it to you. E-4. And you can find your pH that way. So it is 1.4 E-4. Oh, no, that's the Ka. You have to take the pKa of that. Negative log that first. 1.4 E-4. You log it. I got 3.85. Okay. Remember, if these two are equal, you would have the same pH. But they're not. They're a little bit off. So I'm going to go ahead and do this math. 0.1 divided by 0.12. They're a little bit off. Log that. I got 3.85. I got a minus 0.0792. Subtract those. 3.77. So it's close to pKa still, but just a little bit off because they're not equal. Easy, right? Okay, your turn. Go ahead and try this. Pause the video. Okay, so this one's a little bit different. It says how many moles of NH4Cl? So again, this is a minus, that's a plus. I'm going to use that. I'm going to ignore the Cl minus. Must be added to, so NH4 plus would be the acid or the base. NH3 is the conjugate. These are conjugate pairs. So the one with the H plus, with another H is the acid. So that's going to go in the bottom. Okay. And the acid would be, oh no, I'm sorry. Yeah, the base would be NH3. Okay. How many moles of this must be added to 2 liters of 0.1 molar NH3? So you have 0.10 molar NH3. Oh, first let me get the pK. Oh, okay. Let me use that later, okay? To form a buffer whose pH is 9.0. So they gave you the pH. And you can find the pKa here. What I'm going to do is go to the appendix D to find the pKa of NH4+. NH4+ won't be here. It'll be in the conjugate base section right here. NH3. The conjugate acid is NH4+ right here, which means you're going to do Kw divided by 1.8 E-5, 1.8 E-5, and you're going to get the Ka that way, okay? So 1.8 E negative 5. So Ka is equal to 1 E negative 14 divided by 1.8 E negative 5 is equal to 5.56 E negative 10. That's the Ka. pKa is equal to, take this and take the negative log of it. Okay, so that should be 9.25. Okay, so that goes here, 9.25. So you can see you're a little bit off. That means you have to change this a little bit. Okay, so it says that you have 2 liters and you have 0.1 molar NH3. Okay, so I'm going to put that molarity here. Okay, so 9.00 equals 9.25 plus log of the molarity of NH3 is 0.10. Remember that what I plugged in is molarity, okay? Which means whatever I solve for here is going to also be in molarity. Okay, that's molarity as well. Okay, so I'm just going to move this to this side, so negative 0.25 equals log of 0.10 over x. Just solving for x, the opposite of log is anti-log, which is 10 to the power of that and 10 to the power of that. Okay, so what that will do, it'll cancel the log. Okay, so once you do that, you're going to get x is equal to 0.18. And what you found is the molarity, which is moles per liter of NH4+. Okay, and so it's asking for how many moles of NH4+, which is the same as NH4Cl because they're 1-to-1 ratio, right? This is the number of moles of NH4Cl as well because they came together, right? So I'm just going to do that. So multiply that by 2.00 liters, or 2.0 liters, just 2 sig figs, it'll give you the moles. So I got 0.36 moles of NH4Cl. So this is pretty powerful. What I've done is this. Let's say I want to use NH4+ and NH3 in my buffer, but I look at the pKa and the pKa is 9.25, and I say, well, if I add equal amounts, I'm going to get 9.25. But what if I really want a buffer that's pH 9? Then I just have to tweak these two a little bit, add a little bit of one more than the other, and then you can pretty much get what you want. You can get a buffer that's pH at 9. Okay? Okay, pause the video and try this one. Calculate the concentration of sodium benzoate. So here, Na+. Benzoate must be this right here, because that's benzoic acid, so that must be the benzoate ion. C6H5COO-. So that is what I'm concerned about. I can ignore that. That must be present in 0.20. That's supposed to be a big M. Okay, sorry. Molar solution of benzoic acid to produce a pH of 4. Okay, so I'm going to use pH equals to pKa, Henderson Hasselbach, plus log of Va. Okay, so it says calculate. You want a pH of 4, so put that here. So you have to look up benzoic acid on the appendix D. I think they're alphabetical over here. 6.3 E negative 5. That's the Ka. Take the negative log of that and you're going to get the pKa. .20. So if you just put equal amounts of acid and base, conjugate acid and base, you're going to get a pH of 4.2, but you want a 4.00, so you're going to have to change what you put in there a bit. It says calculate the concentration of sodium benzoate. So sodium benzoate is the acid or base? That's right, it's the base. So this is this, so that's missing. That must be present in 0.2 molar of the acid, so this would be 0.2. And that's your math problem. Again, you just put this to this side, 0.20 equals log of, this would be your x on the top, over 0.20. Okay, power of 10, power of 10. This cancels. 0.63 is equal to x over 0.20. X is equal to 0.13. So what I found is the molarity. Molarity of the base, which is sodium benzoate. CH3, COONA. You can put Na, you don't have to, but it's not going to do anything. But that's the answer.